These are basic blocks of quantum computation and quantum information theory. So what is a qubit? So any two-level system called a qubit. So it should have two levels. For example, the polarization of a single photon. Polarization can take two orthogonal directions, two orthogonal states like horizontal and vertical, or diagonal and anti-diagonal, or left and right circular polarization. So there are two orthogonal states of polarization, and a single photon can exist in any superposition of those two orthogonal states. Then we can consider atoms with two energy levels. We can't like have atom with just two energy levels, so we just focus on two energy levels, we interact with those two, and we disregard the other levels. So in that way we can treat an atom like a qubit. Then we can have quantum dots. We can design quantum dots where the two levels are of interest and we disregard all the other levels. Again, we will have a qubit. We can have a single photon existing in a superposition of two waveguides. The single photon can go to one waveguide or the other waveguide. So two paths, let us say. So this is called dual rail qubit. This is also another example of a qubit which is used commercially as well as in the foundational research. Other is the superconducting qubits. Using the Josephson junction and squids, you can realize a system where the two states can be faithfully recognized, identified, and that can be used as a qubit. All the commercial quantum computers are based on superconducting qubit at the moment. There are qubits with neutral atoms, or there's quantum computers with neutral atoms or ion traps or photons also, but the most successful so far is the one with superconducting qubit. So mathematically, the state of a qubit psi belongs to a Hilbert space, which is a two-dimensional Hilbert space, two-dimensional vector space. So it means there can exist at most two mutually orthogonal states. Like we said, the polarization of a single photon, we have horizontal and vertical. So there are only two at a given time. There are only two orthogonal polarizations. So the H2 or two-dimensional Hilbert space is the defining or the vector space belonging to the qubit. So of course the states are from the projective Hilbert space. So that will be CP1, complex projective, one-dimensional. So a state psi in the matrix form will be a two-dimensional vector, alpha and beta, where alpha and beta both are complex numbers. So the state psi should be normalized. So psi inner product psi should be 1. That comes out to be alpha mod square plus beta mod square equals 1. That's the normalization condition. Now both alpha and beta are complex numbers, so we can write them in the polar decomposition, like alpha to be exponential of I delta and beta equals b exponential of I gamma, where a and b are real numbers, delta and gamma are phases. So in that way we can write any arbitrary alpha and beta in this form. So the normalization condition turns out to be a square plus b square equals 1. So instead of calling them a and b and this normalization condition, we can just call them cos of theta over 2 is a and sine of theta over 2 is b. Why over 2? It's more traditional and it will be useful in many in some geometrical representation, but this by 2 is not really mathematically relevant, but it's good for some simplifications later on. If we once we say a and b are cos and sine functions of the same parameter, then a square plus b square equals 1 is automatically satisfied. Then because of the ray property of the state psi, a state psi and a state psi prime equals exponential of I theta I zeta psi represent the same physical state of a quantum system. So it means we can first write a exponential of I delta, b exponential of I gamma. This state is same as a b exponential of I gamma minus delta, and it is same as a exponential of I delta minus gamma b. In all three, what we have done in the second one, we have just taken exponential of I delta common and forgotten about it. And in the third one, we have taken exponential of I gamma common and forgotten about it. So if we say we can stick to this notation because that's again very traditional and convenient, and we call gamma minus delta to be theta. So psi becomes cos of theta over 2, not theta, let's say phi, we have already used theta, and sine of theta over 2 exponential of I phi. So we get a canonical form of a state of a two-level system, and that is cos theta over 2 sine theta over 2 exponential of I phi. So here theta is between 0 and pi, and phi is between 0 and 2 pi. That's just to avoid repetition. This was about states. Now next is the observables. Two by two Hermitian matrices represent the set of all the observables for a two-level system. So the base is this 2 by 2 set of Hermitian operators also forms a linear vector space. And the dimension of this can be calculated. We just write it. Dimension of this is 4. The basis for it can be chosen anything, but we choose something more particular. It's called Pauli operators. This will be used extensively in the later on studies. So these are the 4 operators: identity, sigma x, sigma y, sigma z. Sometimes we call them sigma 1, sigma 2, and sigma 3 also. The definition of these are: identity is just 1, 0, 0, 1. Sigma x is 0, 1, 1, 0. Sigma y is 0 minus I 0. And sigma z is 1, 0, 0, minus 1. This is how we define the 4 Pauli operators. So these operators being bases means any Hermitian 2 by 2 operator A can be written as sum over mu from 0 to infinity, not for 0 to 3, A mu, sigma mu, where sigma 0 is identity and sigma 1, 2, 3 are defined up there, and A's are the real vectors. A mu is a real number. So if we expand it, it will look like A0 plus A3, A1 minus I A2, A1 plus I A2, and A0 minus A3. We can see that once A1, A2, A3, and A0 are real, then this is a Hermitian operator. And we can also see that if we are given a Hermitian operator and arbitrary Hermitian operator, we can always find A0, A1, A2, and A3 for that operator. So this becomes the representation of a Hermitian operator, or decomposition of a Hermitian operator in terms of Pauli matrices. The expectation value of A is in a given state psi is A psi, which will become sum over mu, A mu, sigma mu. So if we are given psi to be cos of theta over 2, sine of theta over 2, exponential of I phi, then we can calculate sigma x. It comes out to be sine of theta cos of phi. Sigma y expectation is sine of theta sine of phi, and sigma z expectation to be cos of theta. So in that way, for a given state psi, we can calculate the expectation values of sigma x, sigma y, sigma z. Expectation value of identity is 1. And so from these three expectation values, we can calculate the expectation value of an arbitrary observable in lab. One interesting example of such operator is the Hermitian operator is the Hamiltonian. So let us represent it by h, and this will be again mu from 0 to 3, h mu, sigma mu. So we expand it, it becomes h0 plus h3, h1 minus I h2, h1 plus I h2, h0 minus h3. So this is the most general Hamiltonian we can encounter for a two-level system. Now we are interested in the eigenvalues of the Hamiltonian that will tell us the energy levels of the system. So the eigenvalues of H can be calculated and turns out to be H0 plus minus root of H1 square plus H2 square plus H3 square. So it means we have two energy levels. One is the lower one, let us call it ground state. And one is upper one, let us call it excited state. The energy of the lower one is H0 minus root H1 square plus H2 square plus H3 square. And the energy of the upper one is H0 plus H1 square plus H2 square plus H3 square. So we can shift the energy of the whole system in such a way that the center comes in the zero comes between the two levels, exactly between the two levels. So that the separation, this separation and this separation is same. So in that way, we can get rid of H0. So it means we can, the Hamiltonian H and H prime equals H minus H0 times identity will give you the same result. Will have the same behavior. Now we can call this energy as E over 2 and this as minus E over 2, or this is H bar omega over 2 and this is minus H bar omega over 2. So, and we can represent excited state with E and ground state with G. Then the Hamiltonian becomes these are the eigenvalues, so minus H bar omega over 2 G plus H bar omega over 2 E. This becomes the canonical form of a Hamiltonian for a two-level system, where G and E are the eigenstates and H bar omega is the energy separation between G and E. Now if we choose G to be 1, 0 and E to be 0, 1, that is the eigenvectors of sigma z, then our H becomes minus H bar omega over 2 1, 0, 0, 0 plus H bar omega over 2 0, 0, 0, 1, which comes out to be H bar omega over 2 sigma z. So any Hamiltonian, if there is no preferred basis for a Hamiltonian, then the Hamiltonian of a system, of a qubit system, can always be taken as some multiple of sigma z. That's the simplest Hamiltonian we can choose if there is no preferred basis. If there is preferred basis, then we of course have to choose G and E in that basis. Otherwise we can choose it eigenstate of sigma z, and that sets the basis, and then everything else can be represented in this basis. Next is the time evolution. So the Schrodinger equation does not change with the dimension, so it's where h is the Hamiltonian, and if the Hamiltonian is time independent, then psi of t is exponential of minus I over h bar, h t minus t0, psi of t0. Now exponential of the Hamiltonian we can write as minus this is I omega t minus t0 gg plus exponential of minus I omega t minus t0 ee acting on psi of t0. If psi of t0, the initial state, is cos of theta over 2 ground state plus exponential of I phi sine of theta over 2 the excited state, then the state at time t will be exponential of I omega t minus t naught cos of theta over 2 g plus exponential of I phi exponential of minus I omega t minus t naught sine of theta over 2. So in that way we can calculate the time evolution of a two-level system.